Before our session actually starts today, I'd like to just introduce you to something that I think might be useful for you. We've got this concept up here of top 10 releases, and I just want to show you what's inside there. So if you go to our main page, go to top 10 releases, it's going to take you to 10, in fact 11, because we've got a 0.5 down there of releases that we've made over the course of this last few weeks. So we'd like you to go and have a look at it. The first page is going to bring you to is actually the one I want to draw most attention to you guys, and that is the EverLearner UK Tour 2018. And there's lots of information here, but the thing I want to get to at this point is that what we're doing is we're putting on a series of 10 classroom demonstrations in 10 different schools across 5 days in July. And if you'd like to host us in that tour, all you have to do is come in and fill this form in and submit it, and then we'll look to see if we can incorporate you into that tour experience. Now then, interestingly, we've got a situation here where we've got numerous other things we'd like you to be aware of. The autumn sale, which to be fair is now past, new GCSE courses, new A-level courses, the new Cambridge Technical, feedback that we've added, the Biomechanics course that you guys already know because you're involved, the roadmap, the fact that we've now got courses for WJC, the new website that we've got arriving very, very soon, and perhaps most importantly of all, we've got the secret master plan down here that talks you through an unbelievable level of detail about what we're going to be doing as of January 2018, and go and read it. It's going to be a significant time for all of us if we manage to get that right. It's going to be something which is going to be a game changer, we think, for a massive number of people in our sector, and we urge you to go and read what it is that's written here in this secret master plan just between you and me, just so you can have a look at what it is we're actually trying to do. So look, I graciously and humbly ask you to come and have a look at these things. If you'd like us to come to your school and demonstrate the classroom model that we've talked about on a number of occasions already, get involved and put your name on this form and come and actually take part in that with us and see it for yourself. See it for yourself what that event is actually like, what that classroom is actually like, and we're confident that you're going to really value that experience. So we're going to get on with the session shortly, but for now, please come and have a look at top 10 releases on the main website. And hopefully there's going to be something in there to kind of tweak your interest. Cheers. So we think we are live. Anna, are we on? Are you confident we're on and we're live?
Yeah.
Yeah, you're happy with it. So good evening, one and all. We have a new team with us this evening. Anna, I don't know if you're going to show yourself on the screen, are you? Feel free. So this is Anna. Anna's on the decks for us right now, and she's going to be with us. Say hello, Anna.
Hello.
Anna's a good friend of mine, and feel free to put me back on, Anna. Look, a couple of things before we kind of get started. We've got a long session tonight with a lot to cover, so I'm basically going to dive straight into it. Please make sure you've got your notes. You're going to need those because there's very, very specific applications within there that you need to be looking at. Secondly, please also make sure if you're willing to, it'd be really appreciated if you subscribe to the channel and you gave us a thumbs up and a like. I mean, only if you want to, of course. I mean, it's completely your decision. And that thing we just put up there about the tour hosting, if you're interested in that, I mean, we'll literally come to your school and we'll demonstrate a classroom model within your school in the summer term. And we did it last year with 10 schools, and it was really, really successful, and people really liked it. And one of the very, very practical thing right now, you're right, Anna, one of the very, very practical thing is that for this session this evening, it'd be really good if you've got pens, some pencils, and a ruler with you, because you're going to need those right now. So it'd be good if you've got those. So with that all said, let's get on with it. And Anna, if you could push us onto the main part, please, that would be really great, and give me an indication when it's done. So here we are once more. Let's make a start. Look, we're on vector drawing and resultant forces, and we're really interested in how we'd go about teaching this thing. So I guess for me, I want to talk about the key skills of this vector illustration, and also I want to look at conceptually this idea. Now, the vector illustration is applied slightly differently by different exam boards, but if we look at key principles here and get the key concepts across, then I think that will be the important thing. Now, look, try and get my words out. Now, look, you guys already know about our classroom model. I'm not going to go on about it in any great detail here. The only thing I would say about that classroom model is please be reminded that we work in this classroom model all the time and we find it incredibly effective. We're going to be soon publishing some really significant studies and results on the massive impact this classroom model, if done well, can have on student performance. But I just wanted to tell you something on an anecdotal level, really. One of the things that clinched my mind forever that I was going to move, well, not forever because it might change, but that I was going to move in this direction of a classroom is that one of the first times I tried it in this specific model with students working self-paced with the four zones, with the terminals, the tutorials and the doing and the practice, was actually when I did a formal lesson observation on vector drawing. So it is kind of close to my heart, this particular episode, as it were, because when I did that, it was by far the most successful lesson that I've ever done in that kind of formal observed condition. I actually had two observers in the room, so there was an observer observing the observer, and it's fair to say that it went well. And so what we had the students taking their core tutorials here for the core process. They were studying the ideas, and we'll look at some of these resources in a moment of vector illustration. They were practicing drawing, sticking, gluing stuff over here, and when students got stuck, I supported them over here. And you'll be able to see how that kind of builds into the resources that we're using today. But all that being said, the first thing we're going to do is we're going to quickly review our center of mass from our previous material. Okay, so we didn't do these past paper questions last week, so let's quickly do them now. So we've got a question here which is to define. Now, when we define, we're saying what that thing is. If we were to look at our roadmap, we would say that it is, or it's the process by which. So we literally want to say center of mass. I'm going to use orange here, is, and there's my kind of key connective that shows that I'm defining, showing that this is what it is. It is when mass is distributed equally in all directions. Or I should have put the point of the body equally in all directions. Okay, so I probably should have put there that it's the point of the body where mass is distributed equally in all directions. In other words, I'm taking one of my three key definitions from our last session, and I'm implementing it straight into the exam in the form of a definition. Now, this question, I'm not sure we'd get an exam question. It's more of a skills question here. Estimate the performer's center of mass in the following example. Illustrate it with a dot. So I want to get some kind of red dot, and I'm illustrating it over here. So the key principle I want to think about here, and we can all have slightly different opinions about where the center of mass would be, is that the head, which is heavy, is low and sort of under the line of the body and under the navel point where we tend to put the center of mass. The two legs are likewise below that level, so I'm thinking about it like that. Although the arms are kind of above, but the arms are not as heavy as the legs. So the key thing I'm thinking about the center of mass position here is that it's come downwards from the navel to the sort of back of the body. And I'm going to suggest that the center of mass, I'm probably exaggerating a little bit, is in this position here, because these objects of mass are actually arced and below that point. So the mass distributed equally in all directions, or the concentration of the matter, is going to be that sort of just outside the body position. Now, in this particular example, I don't think we could justify bringing it down here, for example, because she's not arced enough. If she was really arced, think like a sort of like a rainbow sort of inverted U shape, then we might get the arc to be further down here. But I think with what we've got here, we're going to be talking about our center of mass in approximately that position. Now, we've got another question over here, and this is where I want to spend a little bit longer. Explain why the long jumper raises their arms during the long jump. So we see here, at the point of takeoff, the arms are coming up in that sort of action there. And we want to immediately say this is because, and of course we're crossing because bridge. When we explain, we use because to show that we explain, especially explain why. This is because we're going to put it raises the center of mass. Okay, so there's our 1 point. That's going to get us, in a few moments, that's going to get us a circle a tick and 1 mark for that point, but we've got to get another point here. So I'm actually going to go into a little bit of theory before I actually put the answer in. When we look at a heavy object, let's say the center of mass of a long jump, let's say that's the center of mass of this performer here. So it's going to be like this position here. The center of mass of the heavy object, actually by definition, when it becomes a projectile, it travels in what we call a parabolic. It travels in what we call a parabolic shape. Okay, so any heavy object, when it becomes a projectile, think of a human body, think about shot and shot put, more of which later on, it ends up having a parabolic, or what we call a symmetrical flight path. So that becomes very interesting, because that means that as soon as the center of mass, as soon as the body leaves the ground, at takeoff, what that means for this performer is that the flight of the center of mass, is predetermined. So I want you to sort of get your heads around that. We're going to talk about it more within the session. But it actually suggests that what we've got here is that once the toe leaves the ground, the flight is predetermined. No matter what happens, the center of mass is landing there. So therefore, theoretically, if the performer can raise their center of mass to slightly higher at takeoff, look what happens now. I'm going to try and do roughly the same curve. We're saying the force is the same. Look where the center of mass lands now. It lands a greater horizontal distance from the takeoff point. So raising the center of mass means that there's an extended horizontal flight of that center of mass. So we could put, and this again, this is one of our key connectives. This means that we're explaining. So this means is one of our key ways that we can explain by saying this means. Therefore, comma would be another alternative. This means the center of mass travels and now go to our answer, greater horizontal distance. And if they travel a greater horizontal distance, what does that mean? They jump further. Now, we'll get into a bit later on the fact that even in this situation, let's go back to our long jump, but look what they're doing. Their center of mass, look, is landing. Here's the center of mass. It's going to land sort of here. And look, they're trying actually to land, get their feet ahead of their center of mass, so they even travel further than their center of mass. Now, it looks to me like this jumper landed right on their bum, so maybe it didn't work out for them on this occasion. But in this occasion, they raise their arms and their one knee of their non-takeoff leg, so they can raise the center of mass, so they get a greater horizontal distance traveled. Beautiful. Let's move on to the main part of today's session. So we're going to look at teaching vector illustration. So just as a clarification, we're talking about vector drawing. We're talking about pin diagrams. All of this is basically the same stuff, pin diagrams. We're talking about force diagram. What have I done there? We're talking about force diagrams. So all of those are synonymous. And what we're going to do is I'll come to the rules in a second. Let's just do a worksheet for intuition. So here's a worksheet. I could look at this, and your students might look at this, and they might have absolutely no idea what this concept is, and they could do this first. We find this is a really useful and facilitating thing for them. So what happens? The student has a look at question number 1. Let me just move close to the microphone slightly. The student has a look at question 1, and what do they see? They see that a little up arrow plus a little up arrow equals a big up arrow. Now, we might want to remind our students here what equals means. I know it sounds very base, but what does equal means? It means that whatever's on either side of that equal sign is exactly the same magnitude, and in this case direction too. Okay, so if we think about it, we've got 2 little arrows that if we add them together it makes a big arrow. If I was to go, right, if I made this into numbers, let's call that arrow there is equivalent to number 1. That arrow there is equivalent to number 1. And what does that make this arrow? Well, it would make that arrow a number 2, a bigger number, right? Because it's 1, add 1 equals 2. But the other point we'd make is they're in that direction, because if we had 1 plus minus 1, this arrow, of course, would be in the other direction. Anyway, that's what we've got here. So here we've got a little up arrow plus a little down arrow equals what? And often students get stuck at this. It's like, well, it equals nothing. That's the answer we're looking for. It equals 0. And the point we want them to make, ideally, they might not do this to begin with, is 0 net force. So now they start to think, right, these arrows are about forces. Let's have a look at this one. A little up arrow plus a big down arrow is going to make some kind of little down arrow, correct? Okay, so that little down arrow is going to be important in this example. Now, one of the things I'd say for you guys as the teachers is that I would get you to literally measure the size of these arrows to the tip of the arrow and make sure that they are absolutely correct. What's this one going to be? It's going to be a little up arrow. What's this one going to be? We've got a little up arrow, a little down arrow, a little up arrow. So what do we end up with? A little up arrow, because we've got 2 of those. This one's an interesting one at the bottom because you have to make the equals is a big up arrow, a vertical up force. So in this case, you could put something like this plus 0 would be perfectly fine. Or let me just give you an alternative. It could also be equal to a little up arrow plus a little up arrow. Or you could do a little small arrow and a really long up arrow, for example. Now they're the vertical ones. The horizontal ones work in exactly the same way. I don't think I've got this exact red color, but this is going to lead obviously to a long horizontal arrow in that direction. This is going to lead to 0 net 0. Why have I written that way? This is going to lead to 0 net force. This one here, we've got 2 to the right, 1 to the left, so it's going to equal something like that. This one's going to equal, I've done that again. This one's going to equal 0 net force because they all cancel each other out. And this one here, this is going to be a 0, little arrow plus a 0 equals a little arrow. And number 12, we've got this thing here. So let's go for I don't know, let's go for a longish one of them plus a middle-ish one of them. You get the idea. You can make those last ones up. So the point we're trying to make with the students is that in these examples, we have a situation, where we're looking at the product of different vectors. And I would really like to stress to you what a vector is. A vector is a force that has 2 things. It's a force that has a direction, okay? And you can see here, all of our arrows have a direction because they're pointing in a certain direction. And it has a magnitude. A magnitude is determined by how long the arrow is. If the arrow is longer, it's bigger magnitude. Magnitude, by the way, another way of putting that is just size. So a bigger the arrow, longer the arrow, the greater the magnitude. So let's put it into an example. We have got in fact, before we do the example, we've got some rules before we start looking at examples. The rules we're going to follow, we'll actually come back to this once we've got an example in place. The point of origin of our vectors must be correct, they must be labelled, and they must have direction of movement. So let's have a look at this performer here. First of all, let's acknowledge that probably what this performer is doing is they're probably in the ready position. They're probably in the ready position. So what does that mean by definition? It means that what we've got is let me put it here. What we've got here is no movement. They're still, they're stationary. They're Newton's first law. They're in a state of inertia. They need an external force to overcome their constant velocity or 0 velocity. So our direction of movement in this example is done. We've got no movement, okay? If there's moving, we'd use an arrow. So no movement. Now we want to put our vectors in place. So we first of all want to address our vertical forces. So let me put my toolbar on. Let me get some lines. Okay, so I'm going to use, let's say I'm going to use a nice red color for the weight force. Now weight force is going to be something like this. Okay, I will make these lines a little bit thicker in a few moments time. I wonder if I can actually do that now. I'll come back to that. So this weight force, which I'm now going to label, so let me label it. So this weight force, I'm going to label it as W for weight force. I want to notice first of all where its point of origin is. Okay, where its point of origin is. The point of origin for our weight force is always going to be in the center of mass. And the reason I say that is that the center of mass is effectively an indicative position which shows that all of the weight of the body is acting downwards, in this case towards the center of the earth. But we're going to illustrate it from one specific point, and the center of mass is the best version we have of being able to do that. Now, so we've got a weight force that comes down. Now, just as sort of a biomechanical kind of behavior, we know that weight force arrows, in terms of their magnitude and their size, if it's of a human being, we tend to find that they come down to roughly the level of the floor between the feet. So that is approximately the right length. If we saw an arrow which finished here in biomechanics, we'd tend to find that that was too short for the weight of a human body. Now what we want to do, let me choose a different color. Let me choose a nice green. Now what we want to do is we now want to show where the reaction forces are. Now my point of origin now for my reaction forces is the contact point between the floor and the foot. And you see here that I have marked on two reaction forces. I'm going to label them GRF. And GRF means ground reaction force. You can just call it reaction force. It's absolutely fine. But we're going to call it ground reaction force because that's what we've got here. Now, what I've tried to do then, I've only done it by hand. You and your students will measure these with a ruler. Is that what we've got now is that plus that plus, what do we have? That big down arrow for the weight, okay, equals, and what would your answer to that be, assuming I've got my proportions right, which I don't think I have. Let me just make these slightly longer. What would you think the answer to that would be after we've done these exercises here? And I'm hoping what you're saying is that that would equal 0 net force. Now, what does that mean for our performer? There's no movement. Our illustration, in other words, our vectors, our vector illustrations show by definition 0 net force, so no movement is occurring. No movement is occurring. Now, can I repeat to you? Please encourage your students to get a ruler out and measure their vectors. I'm pretty confident I haven't made my green ones long enough, have I? So let me just make them a little bit bigger. Let me just make them a little bit bigger because otherwise it kind of looks a little bit silly. So make them a little bit bigger, but your students are going to measure them exactly, because if my ground reaction forces are less than my weight force, what does the illustration show? It shows that my performer is sinking into the ground. Well, they're not doing that. They're balanced. They're at 0 net force. Okay, so that is the main principle. And let me remind you, point of origin must be correct. We've got the center of mass for the weight. We've got the contact point between the floor and the shoes. For the ground reaction force, correct. We never, for example, have a vector from thin air, from nowhere, always from those points. We've labeled our vectors, ground reaction force and weight, perfect. And finally, we must have direction of movement. In this case, my direction of movement is no movement, so that puts us into a really, really nice position. Okay, I'm going to move down to some more complicated examples here, but before I start, I'm just going to take a quick sip of my drink. 1 second. Okay, good. Let's look at some slightly more complex examples here. I'm gonna address this one over here first. And the first point I'm going to make is, again, that this person, we could obviously do them accelerating upwards as they lift the bar here, but I'm going to assume just for now that this example is of no movement. Okay, no movement, and so that no movement, again, we've got a stationary object here, but again, the object in this case is both the performer and the bar combined. This is one body, okay? This is one body combined. So perhaps what we need to do first when we draw in our weight force, we have to decide where the center of mass is. So I'm going to decide that the center of mass is raised significantly in this, and the center of mass is approximately here. Now, you could even make an argument that that center of mass was significantly higher, and I would be happy to accept that. But the point I would really like to get to on this one is that the weight force, and I'm probably going to have to stop when I get to here, is much bigger, much bigger weight force. Okay, so we've got a much bigger, didn't mean to go on to the next illustration actually, it should be okay. So our weight force is now significantly bigger than in the example that we had before. Why? Because we've got this big heavy bar. We could make an argument it should be double. So just imagine, that's actually coming down a little bit further. So what does that mean for our reaction forces? Well, now in our reaction forces, here's our point of origin here. Here's our point of origin here. Well, now we have to have an equal and opposite, N3, law of reaction. We have to have an equal and opposite reaction force to that weight. So we now want our two vertical forces. And again, you guys are going to measure these. We now want our two vertical forces to be equal once you combine them, and opposite in direction, and also label GRF, ground reaction force. So I don't know if I've got it exactly double, but it's there or thereabouts. Please, and do it now while you're taking the session, measure that thing. It would be really nice if we could get that absolutely specific, okay? Absolutely specific. So here we've got a situation where we've got ground reaction forces equal. Now, excuse me. Let me be critically clear. If we had not said no movement, if we'd said, for example, direction of movement up, because the question had been posed that way, this person is driving upwards, then what we'd have to do, of course, is we would make our ground reaction bigger, and now can you see that we've got more upwards vertical force than we've got down force, and therefore this person would be accelerating upwards. Okay, so by definition the illustration would show that they were accelerating upwards. So the example I've just given you here is almost like someone who's jumping, forget the bar or something, it's almost like someone's jumping at this point. They're pushing down into the ground and they're getting a ground reaction force which is greater than their weight force. If ground reaction force is greater than weight force, then we get acceleration up. In fact, let me write that in for you. So if we get ground reaction force is equal to weight, okay, then what do we get? So ground reaction force is equal to weight, then of course we get no movement, okay? But if we get a situation where ground reaction force is greater than weight, then what do we get? We get upwards acceleration. And that, in many ways, is what vector illustrating is for. We are trying to illustrate the motion that the performer is going through. All right, let's look at some other examples, and they get quite complex quite quickly here. So let's have a look. So we've got Bolt here who's accelerating from the block. So first of all, let's stick to what we know, and let's look at the vertical forces first of all. So again, I'll try my red, see if it works in this context. So I'm going to have my weight force coming from a proc. I'm probably going to have to change from red, I think. Let's go for white. So we're going to now have the weight force as we've had it now. Okay, down to the ground for the human body approximately. Labeled. Okay, so there we go. Weight force. That is a W, believe it or not. Now this is where it becomes a little bit harder. Where is the ground reaction force here? Where is the ground reaction force? Well, we're going to say that the ground reaction force opposes the weight force and is on the contact point between the two surfaces. So for us, let me choose a really light blue. For us, we're going to say that the ground reaction force is here. And I'm going to say something that some of you won't agree with at this point. We're going to assume, let me go a little bit further. We're going to assume that there is no vertical acceleration here. Now, I know some of you are going to say to me, well, you know, he stands up and becomes taller. And that's true. And you're welcome to show, if you want to, a slightly greater ground reaction force here than weight force to show that he's accelerating upwards a little bit. But I'm going to make an assumption that he is not accelerating vertically at this point. So what have we got here? We've got GRF equals weight. And as a result of that, we've got zero net vertical force. Okay, so as a result of that, we've not got acceleration upwards or downwards. I repeat again, if you wanted to illustrate acceleration upwards, you would make that one a little bit greater, and it would show he was rising a little bit. Now, this is where it gets really interesting. We now want to put in the horizontal forces, so much more complex than we've done so far. So I want to show two horizontal forces. I want to show friction, and I want to show air resistance. Okay, friction and air resistance. And I want to show the relationship between the two. So the first one I want to address is this actual second one, air resistance. Now, air resistance acts on the entire body, okay, or the frontal area of the body. So therefore, we have to illustrate it from a representative perspective. And on that basis, we are going to illustrate air resistance from which nice representative point? The center of mass. So that air resistance is going to be illustrated from the center of mass. Now, when we think about air resistance, the thing we need to consider is how fast is the object moving? If it's a fast moving object, then the air resistance will be very high. What direction is the air resistance going? Well, we know that if the performer is moving in that direction, we know that the air resistance is going to oppose that motion. So start to think about which direction it would move in, or which direction the force would be in. And also look at this moment in the performance. He is literally at the start. How fast is Bolt? We think about Bolt as a hyper-fast person, which of course he is. But in this moment, is he moving fast? And we have to say in this example, the answer is no. In this very moment, he's moving quite slowly. So there is our air resistance. Just a tiny, I don't know if that's the best color. Let me do that in something else. Let's go for this. This might not help. Let's go for this little greeny color. I'm only hand drawing this. So there is our air resistance arrow. Air resistance. Okay, so air resistance is small. There is some because he's moving and he's moving forward, but it's small because he's not moving fast yet. Now the second one we want to look at is friction. Now friction is the anti-slipping force between two surfaces. Let me repeat that. Slipping is the anti-slipping force between two surfaces. So in this case, which two surfaces are likely to slip against one another? Well, of course, it's the surface of the foot against the ground. So in this case, friction is the anti-slipping force. So if his foot was to slip, it would slip in that direction backwards. So the slipping force, anti-slipping force, of friction is actually going to operate in that direction, and it's going to be a big force because he's pushing hard against the ground. So if we now look at our example, we have got that friction is much greater than air resistance. And what does that mean? It means that we get acceleration. Okay, so friction is much greater than the air resistance, so we get acceleration. We get acceleration forward. Now, I want you to look back at my rules. What have I missed off from our rules? Have a good look here. We've got point of origin must be correct. We're happy. Must be labelled. We've done it. Must have direction of movement. Whoops. So we must, in our example, make sure that we include a direction of movement arrow. D-O-M, direction of movement. Now, obviously, we know he's moving in that direction, but we want to emphasize it. Let's look at what could be an equally complex example here. We've now got Chris Froome. First of all, let's decide what he is doing here. I'm going to assume in this case that Chris Froome in this example is no. Let's say we've already done accelerating. Let's say he's going to move. He's moving at constant velocity. So let's say he's in a time trial and he's somehow in the kind of the middle of his time trial and he's at his top speed. He's not changing speed. So he's at constant velocity. Let's go first of all. Direction of movement. He's going in that direction. Notice he's not accelerating. So you might want to think, well, why don't we put no movement? But he is moving. He's moving in that direction of movement. But now we want to illustrate constant velocity. So let's get started. Weight force from the center of mass. Where? Down to the center of the earth. The bike adds a little bit of weight, but not that much. So there's our weight force. Beautiful, nice. Now let's put our reaction forces in. We've got reaction forces which are from the contact point between the tyres and the road. So we have 1 up, about there, 2 up, about there. Might have got that second one not quite in the middle of the wheel, but you see what I'm trying to do. So there's our reaction forces. R, reaction. Or ground, excuse me. Ground reaction force. And there, if you put the two greens together, it cancels out the red. So what does that mean? We've got neither acceleration upwards or downwards. We've got 0 net vertical forces. Now let's put our air resistance in. Let me use black on the yellow. So let's put our air resistance in. Our air resistance is going quite fast. So our air resistance is pretty long. Okay, so there's our air resistance. Now, I've said constant velocity, so whatever our air resistance is now, it needs to be cancelled out by our friction force. So what colour should I use here? I'm going to go for a little cheeky little blue. So what I'm going to do now is I'm going to say, right, my friction is the anti-slipping force. If this wheel was to slip, it would slip in this direction. So this is the anti-slipping force. So my friction arrow, I'm going to make a deliberate mistake here, by the way. My friction arrow is going to go like that and like that. And if I put those two arrows together, my idea is that they cancel out. There's my friction. there's my friction. So the idea is that those two friction arrows cancel out my air resistance. I might have done the friction too long, so you guys are going to obviously calculate that exactly. Now I'm wondering if any of you can look at that and put it into the chat. What has James deliberately got wrong there, or arguably has deliberately got wrong? And if you're not sure, you should see that all the forces cancel each other out. So we've got constant velocity, we've got a direction of movement forward because acceleration earlier on has occurred. But what I'd like to think about is how many wheels on that bike actually drive and produce friction. Okay, have a think about that. How many wheels actually drive and produce friction? And if you're saying it's just the back wheel, you can make an argument that this weight, friction force here shouldn't be there, and we should just have a longer back wheel friction force. I'll let you guys decide if you want to apply that in that way. But the important thing is, representative, is that the vectors are representative of the forces at play. And if you just looked at the vectors, you would be able to see what this, you'd be able to describe with language what this person was actually doing. Okay, I'm going to take the briefest of pauses just to sip my drink, and we'll get straight back onto it when we're going to move on. In fact, I'm actually going to move down to this worksheet and come back to these examples. I'll show you why in just a second. Thanks. Okay, so what we've looked at so far in many ways is the simplest format of this skill. So, excuse me, I want to quickly introduce the concept of perpendicular resolution before we look at two further examples and look at some exam questions. Perpendicular resolution, let me put it this way. So far, we have sort of asked ourselves, what do we get if we add that to that? And of course, what we get in this case is 0 because the forces cancel each other out and they're opposite one another. Well, what happens if we add that to that? And that's what we will kind of want to address within this next little section. Like, how do we address that issue? So I've got an example here I'd like you to think about. I'd like you to think about the fact that we've got two rugby players. Okay, so here's one rugby player, and this rugby player not only has incredibly long arms but has the ball. Okay, and this rugby player is running, and they're going to hit this point, and you'll see what this point is in a moment. They're going to hit this point, and they're going to be tackled. Now, meanwhile, I've got another rugby player who's over here, okay, and they're going to run, and they're going to tackle our player with the ball. So imagine you're looking from the sky, from a bird's eye view, looking down. The player's running with the ball, the tackler with the long neck is going to tackle them. I mean, they must be good in the line out the way I've drawn that. So they're going to hit this tackle point. So what we're going to get in this situation, let me put some lines in. What we're going to get in this situation is that the player with the ball is going to hit the tackle point with that force there. Okay, so they're going to hit the tackle point with that force there. And of course, that force is going to be some kind of product of their motion and mass, okay, or what we might loosely call momentum. This player is going to hit this tackle point, okay, and they're going to apply the following force. I'm going to make it a much bigger force. Look, it's a really big force. They're going to hit the tackle really hard. Okay, so maybe they're heavier, maybe they're running faster, maybe both. So you see here, the yellow person is hitting the contact with greater force. Well, how do we go about resolving where the resultant force is going to be? And this is how we do it. We use something called, and I always struggle to say this, never mind, spell it. We're going to use something called the parallelogram rule. Okay, so now, if we were to come back to this question, it would help. We've effectively got that question where we've effectively got, what do you get if you add that to that? That's basically what we're asking, right? So what we're going to do here is we're going to form a parallelogram. I'm just going to do it freehand. You will do it with a ruler. So we have to make a parallelogram. A parallelogram is a shape of two pairs of parallel sides. I think I've gone too far there. So you see here, what I've now got is I've got this yellow dotted line is the same and parallel to this yellow force line. Now let me get my green, and I'm going to do a green dotted line like that. And now what I've got is I've got a parallelogram. I've got two pairs of parallel sides. Okay, two pairs of parallel sides. Now you could say it's a rectangle, but they wouldn't always be a rectangle. And what we can therefore do is now we can find the answer to this question, because what we do is we take the force from its origin, okay, and we draw and we draw in a resultant force. And that there is our resultant force. Resultant force. Resultant just means total or net. Okay, our resultant force is in that direction. Now, that's easy enough to see, but imagine, for example, well, let's come to it. Let's actually look it up on the worksheet and you'll see what I mean. So here we've got a job to do. Which of the following quadrilaterals are parallelograms? Well, we know that one is because it's got two pairs of parallel sides. We know this one is because it's got two pairs of parallel sides. So that one is as well. This one has two pairs. This one here has two pairs of parallel sides. This one, what was that? This one, so that one as well has. But this does not have two pairs of parallel sides. These ones are parallel, but the other ones are not. This one does not have parallel sides. Oh, sorry, this one only has one pair of parallel sides, and this one doesn't have any parallel sides. So we've effectively got three parallelograms. Explain why you've chosen them. Because they've got two pairs of parallel sides. Okay, now what we can do now is we can come down to our example down here, and you see we're going to use the parallelogram rule to establish the resultant force for the vectors below. So how would we go about doing that? Well, here I'm just going to freehand draw it. You could do it with a ruler. I'm going to make them into parallelograms. And what does that give us? It gives us a resultant force. Do the same here. I mean, you guys can carry on with this. I don't think you're going to need to. So I'm going to do parallel. So something you guys can actually measure it out. There we go. And you get the idea. You can keep going with these, but we can make our resultant forces in this way. So this resultant force via the parallelogram rule is really powerful, and it's going to help us a great deal right now. So I'm not going to do this one and these two. You get the idea. It's kind of like, I'll just do it quick. It kind of is like that, right? It's like that, right? Oh, I've done that one really badly. It's like, 1 second. So it's like that, right? It's like that. Okay, I'm just doing them scruffily. You can do them with your ruler. But what we can do now is we can come back to our two examples up here. All right, so this one's a really fascinating one. So this involves what we call an action force, this golf example. So let's first of all, the golf ball has a weight. So let's put its weight force in first of all. So let's use our red that we've used already. The golf ball has its center of mass in the middle. I think that's in the middle-ish. And it's got a weight force. It's not the heaviest object, so it has a weight force which is down a bit. Yeah, so it has a weight force which is like that. And we're going to label it weight force. We of course have got a direction of movement arrow as well. We must do that. Now its action force is significantly bigger. So for action force, let me use, for argument's sake, let me use a dark blue. So now we've got an action force, and we're going to assume that this action force is a direct force acting through the center of mass. So now we've got an action force which is from here, but the action force is acting through the center of mass and is pushing the ball in that direction. Now this is where it becomes interesting. We've got that's action, so let's make sure we label it. Now this is where it gets interesting. Do you see we now have the potential to apply this concept to make a parallelogram rule here? So let's do that. Let's make a dark blue. I'm just going to hand draw it. There's a line that's parallel to the action force. Let me get my red. Here's a line that's parallel to my weight force. And now what do we get? We get a resultant force. We get a resultant force, which in this case I'm going to do in orangey color. We've now got a resultant force. And what do we have? We have our resultant force, which goes like that. Okay, so now we have our resultant force, resultant. So that's a really nice model where we can start to express resultant forces when we've got vectors which are not perpendicular to one another. Now you might be saying to me, James, why is there not a ground reaction or a T reaction force here? I'm assuming the ball has just left the T in this example, in case you're wondering. That's my assumption. Another example, we've got Jess Ennis Hill here. By definition, she's going at constant velocity because, as we said before, her feet have left the ground. She's taken off. She's in a state of constant linear momentum. Conservation of momentum is the law that we're showing here. So let's put our vectors in here. First of all, we've got a weight force, center of mass. Okay, she's put her weight back a bit, but center of mass acting downwards, weight force. There's our weight. Now, we've got her air resistance here, okay? Her air resistance, she's a fast runner and she's powerful and she jumps hard, but ultimately she's a human being. Human beings don't move that fast. So the air resistance of this object, I'll do it in black here, is going to be relatively small. Okay, so there's the air resistance. And now what we can do is we can now do our parallelogram. Okay, so we can now do our parallelogram. So in this example, what we're doing here is that let's draw our parallelogram in. Let's draw our parallelogram in. And what do we end up with? We have a resultant force which acts in that direction. Now, you might be thinking to me, well, hang on a minute, James. Didn't mean to do that. You might think, hang on a minute, James, she doesn't move in that direction. And no, she doesn't move in that direction. But this is another concept, and we're going to look at this a lot in the future. What we can say about this resultant force is it's much closer to the weight force than it is to the air resistance. So here we say that the weight force is dominant. The weight force is the dominant force. And guess what? Going back to what we said right up here, if the weight force is dominant, what does this cause? It causes parabolic flight. Parabolic, or let's call it symmetrical flight. And as a result of that, the flight of the center of mass is predetermined. Why? Because it's going to take off about here and it's going to land over here, somewhere over here. It's going to land having traveled through a perfectly symmetrical arc. So again, it comes back to the same point we had before. If the performer can raise her center of mass more at takeoff without losing force, then that center of mass is going to travel a greater horizontal distance. But when she's in the air, in this case, we have the weight force being dominant, and she experiences what we call the law of conservation of momentum. And that means that at takeoff, her flight path is completely predetermined. It cannot change. Let me rephrase that. The flight path of her center of mass is completely predetermined. Okay, we've got a tiny bit more to do. I just want to change the canvas and we'll get on with it. So, okay, we're on the home straight. A couple of questions to emphasize the skills we've learned teaching biomechanics. Bit of a question here on vector illustration. So hopefully you might have even had a look at this. It says, look closely at the image below. The cyclist is accelerating. Identify 2 errors on the vector illustration. So look, I'm not sure, again, we're going to get a question like this in exam. I think we should. I think it would be a really nice application of students solving problems and identifying errors in this case. So I want you to think about the different errors that are in place. Think about the rules that we've applied and we've asked you to apply so far. I'm just going to note down a few before we look at an actual answer. First of all, I want to talk about vector origin. Look at the 2 ground reaction arrows, for example, from the top of the wheels up. Hopefully you should be able to see a problem with that. Secondly, let's also think about labeling of vector arrows, that labeling is not right. It's just not present, and there's no direction of movement arrow. So those are our basic technical parts, but also we need to look at this concept: the performer is accelerating. Well, the issue with that is that on the illustration that we have got the friction is equal to the air resistance, which we know by definition leads to 0 net force, and if it leads to 0 net force, it means that we're moving at constant velocity. So the other criticism we have here is that we're not accelerating. So hopefully you guys can see those things. I've got a written answer. I'll just look at it quickly for you here. So the 2 errors are, we're asked to identify, so we're saying the thing is or they are. There is no direction of movement arrow. That's going to get us a circle. What am I doing wrong? It's going to get us a circle, a tick, and it's going to get us 1 mark. And we've got the ground reaction forces do not start at the ground but from thin air. That's going to get us a circle, a tick and a mark. But we could also say the performer is in constant velocity, for example. We could also talk about the fact that the performer is in constant velocity. And what else did we say was an error so far? We said, the labeling we could have put in there as well. But anyway, we've got 2 and we get our max. Let's move on. We've got a question here, quite familiar. This image shows a 400-meter runner accelerating. Draw all forces acting on the performer at this moment. So key thing is we've got acceleration and our skill is drawing. Okay, so we've already put this answer in for you and see if we can spot the reason why. So first of all, we're going to get circle, tick, 1 mark for direction of movement. Boom, thank you. Secondly, we have got that the ground reaction force, the bigger at the back foot, the smaller at the front foot, are equal to the weight force. So we could write, I mean, we could even explain it, right? So we've got 0 net vertical forces. Okay, 0 net vertical forces. Okay, so that relationship between the ground reaction force and the weight force, it gets us a mark. Okay, so we've got 2 of our 4 so far. Next point, the performer is accelerating, so the friction is greater than the air resistance. We get a mark for that. Friction is greater than the air resistance, and we've got that in place. And the other point I would make is that we're going to get our 4th mark from the fact that our points of origin are correct, and then we get our max. Okay, so that's what's going to get us our max in that situation. Let's move down. Explain why your vector diagram from 2a shows horizontal acceleration only. So we've only got horizontal acceleration. So why is that? This shows horizontal movement only. That shouldn't say that. It should say acceleration. Because it's a clear explaining why skill. Because the weight vector and the ground reaction force vectors are equal. Remember, we said that a moment ago. So we get circle, tick, 1 mark there. Okay. This means, again explaining, there is 0 net force. In fact, let's put these in. So 0 net force vertically, circle, tick, 1 mark. The weight force and the ground reaction force vectors are equal. Let's join those 2 up. Sunglasses, mark. The air resistance is relatively low because, explaining, the performer is not moving very quickly at this point. Not moving very quickly at this point. Boom, mark. The friction generated between the floor and the athlete's shoes is much larger than the air resistance. Therefore, comma, don't forget the comma, there is a positive net force in the forward direction. Circle, tick, 1 mark, max, thanks very much, points in the bank. So we've got a nice, neat answer. This means the athlete is accelerating. I actually think we should have added a word there, horizontally, or we could say forward. Okay, so we do want to mention that direction. Think about Newton's second law. The acceleration is proportional to the force acting and in the direction it's acting. We made a point of that. Let me just get rid of that a second. Next question. Draw a pin diagram of the same performer in the last 50 meters of the race. So the first thing we want to do is in the last 50 meters of a 400 meter race, what are we going to expect? And we're largely going to expect that they're decelerating. Now, I know someone can say to us that if we look at one of Britain's best ever 400 metre runners, Christina Ohurugu, for example, she does not decelerate in the last 50 metres. That's the strength of her performance, that she runs an even pace, and she is the one that slows down the least to win. So, but we're going to look at the average 400 metre runner. They decelerate at the end of their race in that last 50 metres. And if you get that wording in your exam or in the student's exam, that's what they're looking for. So here, really, what have we got here? Draw a pin diagram of the same performer in the last 15 metres. So look, a couple of things. Dom, thank you. Then again, Dom. Thank you. Importantly, we've got the friction force and the air resistance force. The air resistance is bigger. Okay, so we've got air resistance is bigger than ground reaction force. It actually looks quite close, but it should be. Let's put it that way. And finally, we've got vertical forces are 0 net vertical. So the fact that our weight and our ground reaction force cancel each other out gives us our other one, and we have our max. Beautiful. Okay, so there's some nice exam answers there. This one we've already done, so I'm probably going to leave that one for you. This image The image below shows a golf ball at the point of contact. Illustrate all forces acting on the ball, including the resultant force. So I'm going to do it ever so quick, freehand, because we've already done it. Look, here's my weight. You guys are doing this with a ruler and measuring, right? So here's my weight force. Here's my action force. Okay, so here's my action force, correctly labelled. Now I'm going to show my skill of making a parallelogram. Now I'm going to show my skill that I can make a resultant force, not very straight resultant force. And what have I forgotten so far? I've forgotten that I must always put a direction of movement in the illustration that way. Okay, so you're going to do that. You're going to make sure that that's done with rulers, measures, correct. There's a perfect parallelogram. Obviously, if you're asked to explain this, you would say we're using the parallelogram rule, and so on. All right. Final thing from me. I probably should stop here based on time, but let's just do it anyway. So what we're doing here is that this guy here, he's putting this shot, and this shot is going to come down and it's going to land somewhere down here. You see here that the landing height is below the release height. So the landing height is below the release height, which of course is going to be in shot put. But I just want to introduce you to a concept here. Could we take the idea of the shot? Could we take the idea of the shot in flight? And could we now just illustrate it? So what I'm going to do here is I'm going to illustrate it. I'm not going to really explain all of this to you. I want it to sort of leave it hanging for next time. So the first thing we're going to do is we're going to put our weight in. Now this is a heavy object, so we're going to give it a fair old bit of weight. It's a shot, it's numerous kilos, so we're going to make it a heavy weight. And now the only other force acting on this shot, now anyone who's doing AQA level, look away now, because I may need to go over this for you guys specifically in the question answer at the end. And if you do AQA level and do the biomechanics, you know what I'm talking about. But the air resistance here is relatively low. Why? Why is the air resistance? Do the air resistance in green? Air resistance is low. Why? Because it's slow. Because the shot is not traveling fast. So we've got an air resistance which is back in the direction of travel, which is only something along those lines. So there's our air resistance. So let me put it in. Air resistance, weight correctly labeled. Now what do we do? Well, of course, what we're going to do is we're going to provide a parallelogram like that. Something you're going to measure it up. Mine's not quite straight. And then we're going to put in a resultant. We're going to put in a resultant force, which is like that, something along those lines. So there's our resultant force. Okay, now again, let me repeat what I said before just as a reminder. The resultant force, R, is close to W. Okay, so the resultant force is close to W, and I would like you to start to think about what does that mean for the shape of the flight of a shot put. And if we change this, and if we looked at, for example, a shuttlecock, how would that differ for the shuttlecock? So if the result force is close to the weight, what does that mean for the flight path? And if we change this object so that it was a shuttlecock, how would that differ? And that's a really nice introduction to what's to come. Okay, we'll leave things there and let's go back onto the question answer. So, are we back on, Anna?
Yep.
Yeah, so okay, back in the studio, as it were. We're definitely on, yeah? We've definitely got the right feed going through?
Yeah.
Yeah, happy? Okay, great. Well, look, before we start taking a couple of questions, before we start taking a couple of questions, I sort of want to address something, actually. You probably realise that Anna's not normally with us doing this particular job. Normally it's Marta who's with us. Now, Marta, she was supposed to be here tonight, bless her. But she's still trying desperately hard to get back from Barcelona, where she's from and where she spent the last couple of days. And in fact, if you've been watching the news recently, you realise it's been quite a traumatic time over there. Marta spent a really difficult day on Sunday at a polling station all day, and her flights have been cancelled today. All kinds of stuff going on. So, Anna, you've been awesome tonight. From what I can tell, I'll have a little review later, but it looks like you've done really well. So, Anna, put yourself back on and fire away with questions.
Okay, so Tim Brown said, or asked, is there ever a case that you might include drag from tyres?
on a bike?
I think so, yeah.
Okay, so the key things I'd say about drag, we sometimes use this term to mean different things. So drag is synonymous with air resistance. It is effectively the pulling force in any fluid. So when we're talking about fluid or fluid dynamics, we're really talking about two substances. We're talking about, on Earth at least, we're talking about the air and we're talking about water. Now, we would definitely use drag as the term for the equivalent force for air resistance in water. So think that, for example, if we had a vector illustration for a swimmer, we'd have weight force down, we'd have buoyancy, not ground reaction force going up, we'd have action force going forward from the pull of the arm or in the kick of the leg. And what we'd have is we'd have drag coming back from the center of mass, pulling back from the water back on the body. Now, coming back to the specific question, would you ever, if you think about something going very fast downhill, something like a bike, but even better if you think about something like a downhill skier, for example, they might be coming down a very steep alpine slope. And in this case, what we find that there is a force backwards from the underside of the skis, and that force would be friction. And in that case, the potential slipping is forward. So what they would tend to do, so the anti-slipping force is friction, but in their case, they're looking to minimize friction, which is why they wax the bottom of the skis to reduce that friction drag force. But one of the key principles to grasp on that one, Tim, is that when they're coming downhill like this, the weight force is not pointing down that way. The weight force is pointing down to the center of the earth. So effectively, the weight force, at least partially, is pointing down the slope. So yeah, so that's my answer. Other questions, Anna?
Okay, so Ryan Conroy asked, what does it mean by a pin diagram?
Do you know the answer to this one, Anna?
Is it the same as a vector drawing?
It is. That is exactly what it is. That's it. So, pin diagram is effectively it's another way of saying vector diagram or vector illustration. So that's exactly what it is. So we just use pin diagram, vector illustration interchangeably, really. So consider those to be exactly the same thing. So yeah, absolutely use them as equivalent terms. Use them as wide as you can. And I have seen them used quite broadly in exam language. In the past. Now, whether they'll only use vector illustrations, vector diagrams going forward, whether they'll use pin diagrams, it's hard to say. But yeah, that's effectively what it means. Any more questions, Anna?
No, there's none at the moment.
None at the moment. So, I wanted to clarify something which I think I didn't really explain very well. So I want to sort of quickly clarify this, and that is the concept of the conservation of momentum. So if we take the heavy object, if we take something like the shot, if we take the human body, for example, once it's in flight, once it's in its flight path, once it's left the ground, left the hand, what we find there is that its center of mass is going to travel in a completely symmetrical parabolic flight path. So in other words, once it leaves the hand in the case of the shot, once it leaves the floor in the case of the foot on long jump or high jump, for example, the flight path of that center of mass is following the principle of the law of conservation of momentum. So the center of mass flight path is completely predetermined. So I think a couple of images I like that help me think about that. You see those like shot putters, and they put the shot, it goes out there, and they're kind of screaming after that shot. It's kind of symbolic to me because there is no other force that can possibly act on that shot. I mean, it would need an unbelievable gust of wind to have any kind of impact on that, for example. Likewise with the jumper. Once they're in the air, their center of mass is landing in a specific point. And what they're going to do is they're going to try and manipulate their landing touching point, their feet probably, to move ahead of that center of mass, and then they'll rotate around so that their center of mass, although it's landing behind them, they're sort of rotating around it to miss the sand at that point. So it's a fascinating aspect of the technique. So yeah, I thought I'd better just clarify that for you. So a couple of sort of organisational things, and I do fire away with any other questions if they come in. Okay,
Yes,
couple of organisational things for you. As always, we will post the recording of tonight's show We'll put it onto the on-demand course, and the notes pages are already in there, but the notes pages will be there as well, so you can keep using that as you like. There's loads of practice questions on those vector illustrations on there, so you can go and have a bit of a play with those and sort of have a bit of a practice with what you've done. And also, of course, the resources that we've used in the session are all available in the resource pack, which you guys have already got available. So, what we're going to do is, Anna, in a second, if you remember what we said we were going to do at the end, you're going to fade us down to black and take the sound down. And as you do that, I am also going to stop the stream once you give me the signal. So from James, massive thank you for being here this evening. Anna, anything you want to say before we finish off?
No.
No, I want to say something. I just want to say I'm really, really proud of you. It was fantastic. And you're making an appearance as well. So this is what happens when mums don't come home from Barcelona on time and their flights get cancelled. We don't cancel stuff because we try and keep things on and put them together, and we somehow patch it all together and make it work. Right? Not bad, not bad. Thanks everybody. Have a cracking evening, and we'll see you. If not soon, we'll see you next week. Cheers, guys. All the best.